Hello everyone, my name is Bita. Thanks for joining today's presentation by Dr. Yajie, who is Associate Professor in University of Central Florida and co-founder of QLEDCures. He will give us a talk on quantum dot light emitting diodes for photomedicine. He will share their progress on flexible QLEDs development and photomedicine studies at the University of Central Florida. Meanwhile, if you have any question, please post them in the chat box in the right-hand side. We'll get to them right after the talk. Okay, thank you, Dr. Dunn, for joining with us. This stage is yours.
Thank you, Peter, for the nice introduction. My topic today is on QLED for photomedicine. Thanks to Samsung, probably everybody by now already know QLEDs, but also thanks to Samsung, so there's a lot of confusion in the field. People probably understand QLED quite differently. So we need to explain what exactly QLED I'm talking about over here means. In fact, what I talk about here is not the QLED like Samsung's TV. So what I talk here is you can consider it the advanced OLED, replacing the emitters with quantum dots. By replacing organic emitter with quantum dots, you can bring a lot of benefits of the quantum dot colors. So the most, I would say, prominent feature of QD is because of the quantum size confinement effect, you can tune the quantum emitting to precisely whatever colors, and it's a very pure color. You can get highly saturated, vivid colors. So that's the reason actually for the display world. A lot of people are actually interested in QLED for wide color gamut displays. Over here, I listed a brief summary of the industry status of QLEDs. You can see over here, there are several prominent features. So one thing is, in generally, for QLEDs, they have a lower turn-on voltage comparing to OLED. So that also means QLED, you can probably get to higher brightness comparing to OLED. And also in terms of the efficiency, so the cadmium-based QLED efficiency are close to the best OLED we can get today. Cadmium-free one, a little bit worse, but it's also catching up. So in fact, the biggest challenge for QLED today for display, it remains to be the lifetime. You can see over here is red devices normally have relatively good lifetime, green a little bit worse, blue far behind. Even the most recent progress by Samsung, they reported a relatively long lifetime for blue QLED, but still not sufficient for display. In fact, last year, November, BOE reported the first inkjet-printed QLED TVs, but this is just a prototype, not really ready for the display yet. And you also can see is they are trying to use mostly the red and green color. You cannot really see blue color in their demo chips. So that's actually reflected, as I summarize over here, QLEDs, electroluminescent QLEDs, already demonstrated very high brightness, much higher brightness comparing to OLED. You can have better tunable colors and with much narrower full width half maximum. Like OLED, you can also get flexible form factors, and QD's response time in general is faster than phosphorescent OLED. You get a faster response in nanosecond scale instead of microseconds because quantum dots can be solution processed. So it means the cost, intrinsic cost of QLED can be much lower than organic light emitting diode devices. So that was the benefit QLED field already demonstrated. But on the other side, the limitation of QLED is, as I mentioned, the first color is not balanced. Red is great, green worse, blue is far behind. And in general, their lifetime remains to be short. Of course, in the community, we're also trying to develop a longer lifetime QLED, trying to develop a better blue QLED. But meanwhile, we are also looking at QLED from a different angle. So we are thinking of, with all the advantages we already have, can we take it as a unique solution to solve some problems? I mean, the state-of-the-art technology can already solve. So that's the reason we actually look into photomedicine. Photomedicine is the field